Imagine a massive explosion on the sun, 1 billion times more powerful than any atomic bomb. This colossal burst of energy is known as a solar flare, and it is one of the most awe-inspiring phenomena in our solar system. When these flares erupt, they release a tremendous amount of radiation and charged particles into space. This is a solar storm, a cosmic event that can disrupt our modern world. These storms are not just random occurrences, they are the result of complex interactions within the sun's atmosphere. The sun's magnetic field plays a crucial role in these events, twisting and tangling until it snaps, releasing energy in the form of solar flares and coronal mass ejections. These storms are a reminder of the immense power of the sun and its influence on our planet. The energy released during a solar storm can be equivalent to millions of nuclear bombs exploding simultaneously. This energy travels across the solar system, impacting planets, moons, and even the far reaches of space. While beautiful auroras may dance in the sky, these mesmerizing lights are actually the result of solar particles colliding with Earth's atmosphere. The charged particles from the sun interact with our planet's magnetic field, creating stunning displays of light that can be seen near the polar regions. However, solar storms can also bring chaos to our technology-dependent lives. The same particles that create auroras can also interfere with satellite communications, GPS systems, and even power grids. A particularly strong solar storm has the potential to cause widespread blackouts and disrupt our daily lives in ways we might not expect. The sun is not a quiet neighbor. It is a dynamic and ever-changing star, constantly emitting energy and particles into space. The surface of the sun is a roiling sea of hot plasma, with temperatures reaching millions of degrees. It is a giant ball of hot gas constantly in motion. This motion is driven by the sun's internal processes, including nuclear fusion at its core, which generates the energy that powers our solar system. The sun's surface is a chaotic and turbulent place with plasma currents swirling and churning in a never-ending dance. This motion creates powerful magnetic fields that can twist and snap, releasing tremendous energy in the form of solar storms. These magnetic fields are responsible for the sun's complex and often unpredictable behavior. When the magnetic fields become too twisted, they can suddenly realign, releasing energy in a violent explosion. These storms can hurl massive amounts of charged particles towards Earth at incredible speeds. Traveling at millions of miles per hour, these particles can reach our planet in a matter of hours, impacting our magnetic field and causing geomagnetic storms. These storms can have a range of effects, from beautiful auroras to serious disruptions in our technology. Solar storms are not just single events, they are a complex interplay of solar phenomena. These storms originate from the sun and can have significant effects on our planet. Understanding the different components of solar storms is crucial for predicting their impact on Earth. The most well-known components are solar flares and coronal mass ejections, or CMEs. While both are related to solar activity, they are distinct phenomena with different characteristics and effects. Solar flares are intense bursts of radiation that travel at the speed of light. These flares are caused by the sudden release of magnetic energy stored in the sun's atmosphere. When this energy is released, it accelerates particles to near-light speeds, producing a burst of electromagnetic radiation. They can disrupt radio communications and GPS signals. This is because the intense radiation from solar flares can ionize the Earth's upper atmosphere, affecting the propagation of radio waves and causing signal blackouts. CMEs, on the other hand, are giant clouds of solar plasma, a superheated mix of charged particles. These ejections occur when the sun's magnetic field lines snap and reconfigure, propelling vast amounts of plasma into space. These clouds can travel at speeds of millions of miles per hour. Unlike solar flares, which reach Earth almost instantly, CMEs take 1 to 3 days to arrive, depending on their speed and the distance they need to travel. When a CME hits Earth, it interacts with our planet's magnetic field, causing geomagnetic storms. These storms can induce electric currents in power lines, potentially leading to widespread power outages. Additionally, the interaction can produce stunning auroras, also known as the northern and southern lights, which are visible near the polar regions. Scientists continuously monitor solar activity to predict and mitigate the effects of solar storms. By understanding the behavior of solar flares and CMEs, we can better prepare for their potential impacts on our technology and daily lives. The sun goes through cycles of activity, much like a heartbeat. These cycles, known as solar cycles, last approximately 11 years. During each cycle, the sun's activity waxes and wanes, with periods of intense activity marked by numerous sunspots, solar flares, and CMEs. These cycles are not just a curiosity, they have real-world implications. The more active the sun, the higher the likelihood of solar storms impacting Earth. Understanding these cycles helps us prepare for potential disruptions. We are currently in solar cycle 25, which began in December 2019. Scientists predict that this cycle will be particularly active, with a peak expected around 2025. This means that the coming years are likely to see an increase in the frequency and intensity of solar storms. While this prediction is not a guarantee of catastrophic events, it is a call for awareness. The more we understand about solar cycles and their potential impact, the better prepared we can be. Section 5. When the sun strikes. Impacts of solar storms. The impact of a solar storm can range from mild to severe, depending on its strength and the direction of the coronal mass ejection. These storms are caused by the sun's activity, particularly during periods of high solar activity, such as solar maximum. When the sun releases a significant amount of energy in the form of solar flares or coronal mass ejections, this energy travels through space and can interact with the Earth's magnetic field. One of the most common effects is the disruption of radio communications, particularly high-frequency radio used by airlines and emergency services. This can lead to communication blackouts, making it difficult for pilots to navigate and for emergency services to coordinate their efforts. The disruption can last from a few minutes to several hours, depending on the intensity of the storm. Solar storms can also disrupt GPS signals, leading to inaccuracies in navigation systems. This can affect everything from personal navigation devices to the timing systems used in financial transactions. The loss of GPS accuracy can have significant implications for industries that rely on precise timing and location data. In extreme cases, they can induce electric currents in power grids, causing widespread blackouts. These geomagnetically induced currents can overload transformers and other critical infrastructure, leading to prolonged power outages. The most famous example of this is the 1989 Quebec blackout, which left millions without power for several hours. While these extreme events are rare, they highlight the potential vulnerability of our technological infrastructure. As our reliance on technology continues to grow, understanding and mitigating the risks associated with solar storms becomes increasingly important. Researchers are working on developing better forecasting methods to predict solar storms and their potential impacts, allowing for more effective preparation and response strategies. Section 6. Echoes from the Past, the Carrington Event. In 1859, the largest solar storm ever recorded struck Earth. Known as the Carrington Event, it caused telegraph systems worldwide to fail, with some operators reporting electric shocks and fires. Auroras, usually only visible near the poles, were seen as far south as the Caribbean. If a storm of that magnitude were to occur today, the consequences would be far more severe. Our reliance on technology has grown exponentially since 1859, making us more vulnerable to the sun's fury. Section 7. The Quebec Blackout, a modern reminder. The Carrington Event may seem like a distant event, but more recent solar storms serve as stark reminders of the sun's power. In 1989, a powerful solar storm caused a complete blackout of the Hydro-Quebec power grid in Canada, leaving millions without electricity for 9 hours. This event highlighted the vulnerability of power grids to geomagnetic disturbances. It led to significant improvements in grid resilience, but the risk remains, especially with the increasing complexity of our power systems. Section 8. Preparing for the solar storm. While we cannot control the sun, we can take steps to mitigate the impact of solar storms. Governments and space agencies around the world are working to improve space weather forecasting, providing early warnings of potential threats. On an individual level, we can prepare by having a plan for power outages, ensuring we have alternative communication methods, and staying informed about space weather forecasts. Just as we prepare for hurricanes or earthquakes, we must also be ready for the potential impacts of solar storms. Section 9. Respecting the power of the cosmos. Solar storms are a powerful reminder of our place in the cosmos. We are not just inhabitants of Earth, but citizens of a vast and dynamic solar system. The sun, while life-giving, also poses a threat to our technological civilization. By understanding and respecting the power of the sun, we can better prepare for the inevitable storms that will come our way. In doing so, we not only protect our technology but also gain a deeper appreciation for the delicate balance that sustains life on our planet.